All right, today we're going to be talking about graphing rational functions. Now, I'm going to be splitting this section into 3 parts because there is a lot to this. So today we're going to go over some vocab and start to find these points of discontinuity. Okay, so some vocab words first. Continuous and discontinuous. So a continuous graph is a graph with no jumps, breaks, or holes. So if you can imagine, we read a book left to right, okay? That's how we would need to read a graph. So if you imagine an ant crawling along a graph here, okay? So the ant is crawling along from left to right. If they do not fall off the graph, it is a continuous graph. So in this case, our graph is continuous. If I have a graph that looks like this, and the ant is crawling along, right here it falls through. This is not a continuous graph. There is a break in the graph, okay? So we call that discontinuous. Also, a point of discontinuity. That is a point, x equals a, where the function is undefined. Now, when can a function be undefined? That is when the denominator is equal to 0, okay? Or there's some other, if you have a radical, we can't take the square root of a negative number, something that makes this function undefined. For rational functions, it's going to be when the denominator is equal to 0, okay? So we have 2 kinds of points of discontinuity, and I'm going to call them pods from now on. We have a removable pod and non-removable. So a removable, graphically, it looks like a hole in the graph, okay? So up here, let me erase my graph here and make it just a little bit better. Oh, I guess I can't erase it. So over here, if I have, let's see, a graph that looks like that. Right here, I have a hole, okay? It's just missing. Algebraically, which means in our equations, that's whenever you have factors that cancel. Okay, so imagine we're removing them from our equation. We are canceling them. That is a removable point of discontinuity. A non-removable, graphically, looks like an asymptote. Okay, and an asymptote is a line, it's an invisible line on the graph where my graph will never cross it, okay? So that dotted line right there, that is an asymptote. In our equation, it's the factors in the denominator that do not cancel. Okay, we cannot remove them from the equation. Non-removable points of discontinuity. Okay, so these are some vocab words that we are going to work with in this section. Next, I want to show you the parent function for rational functions. It's this equation, y equals 1 over x. Okay, the first thing we need to do is we need to figure out, okay, what number will make the denominator 0? So if you have an x in your denominator, set that equal to 0 and then solve for x. In this case, we just get x equals 0. So x cannot equal 0. That is a point of discontinuity. That is where my function is undefined. Now, I cannot cancel x out of the numerator. So if I can't cancel it, it's non-removable. and that means it's an asymptote. And it's a vertical one. Okay, so on my graph here, I'm going to draw a vertical dotted line at x equals 0. Okay, so my graph is not going to cross that dotted line. So if I just start plugging in some values, okay, let's say I want -2, -1, 0, obviously undefined there. Okay, that's not going to work. 1 and 2. So if I plug in -2 in for x, I get -1/2. So over here on my graph at -2, I'm at -1/2. If I plug in -1, I get 1 over -1, which is -1. Okay, so I'm right there. 0, I'm undefined. Okay, so what the left-hand part of this graph is going to look like is something like that. Okay, now let's look whenever we cross over 0. Let's look at 1. So if I plug in 1 into that function there, I will get a +1. So my point is right there. Then if I plug in 2, I'm going to get a +1/2. Okay, so the right-hand side of the graph is going to look like this. Okay, that is the sketch of your parent function. Okay, now let's talk about domain and range. Domain is your x values. We have this point of discontinuity here. X cannot equal 0, but it can equal everything else. So here's how you're going to write your domain. It's going to go from -infinity to 0, and we're going to put a curved bracket around 0 because it's an asymptote. So that takes care of this side of your graph. Okay, we go from -infinity to 0. Then we hop over that asymptote and we go from 0 to infinity. Okay, so that takes care of this part of your graph. So we go from 0 all the way to +infinity. So a good trick to finding your domain is that whatever your points of discontinuity are, that's where it's going to break up. Okay, so here we only had one point of discontinuity. It was at 0, so that's where my domain is broken up. Now let's talk about range, going from bottom to top. If you notice, my graph, it does something funky along the x-axis. It doesn't cross the x-axis there, okay? That is called a horizontal asymptote, okay? And we're going to talk about that in just a second. But my range, it goes from -infinity to 0, okay? So bottom to top, so we go to 0 here. We don't actually hit 0 because, again, an asymptote. And then we jump over 0 and we go to infinity, okay? So we hop over this and then our graph goes to infinity. So that's what the parent function looks like. Now let's talk about finding these pods. So find all pods. What is the domain of each function? Are the pods removable or non-removable? So here's how you find your pods. You want to factor everything. Okay, so x plus 3 does not factor in the numerator. The denominator does. So two numbers that will multiply to 3 but add to -4, it's going to be -1 and -3. So it factors to x minus 1 and x minus 3. Now, can anything cancel? No. So to find your points of discontinuity, this is what we talked about in class, it's your restricted values. Okay, so you set your denominator equal to 0. So you factor it, and then you set your factors equal to 0, and then solve for x. We'll add 1 to both sides here. You will get x equals 1. Add 3 to both sides over here. You will get x equals 3. So your points of discontinuity are x equals 1 and x equals 3. Now, since they do not cancel out of our equation, these are non-removable. Okay, and so graphically, these are going to be vertical asymptotes. All right, now we need to find the domain. Remember, your domain is broken up at those points of discontinuity, but remember we go from left to right. So my domain, I'm going to start at negative infinity. Now which comes first, 1 or 3? Well, 1 does, so I'm going to go from negative infinity to 1, from 1 to 3, and then 3 to infinity. That's how I'm going to break up my domain. Let's look at a couple more examples. Number 2, we have x minus 5 over x squared minus 1. So that denominator, that's a difference of squares. X squared is a perfect square of x. 1 is a perfect square of 1, so it will factor to x plus 1 and x minus 1. So now to find the pods. Once it's factored, set each factor equal to 0 in your denominator, and then solve for x. So x is going to equal negative 1, and x is going to equal positive 1. Now, can anything cancel? Nothing cancels. So these are points of discontinuity, and they are non-removable. We cannot take them out of the equation. Next, we need to identify the domain. The domain is broken up at those points of discontinuity, moving from left to right. So my domain is going to go from negative infinity to negative 1, between negative 1 and positive 1, and then 1 to infinity. Okay? Last one, number 3, we have x squared minus 3x minus 4 over x minus 4. So, see if you can factor. The numerator, we need two numbers that will multiply to negative 4, but add to negative 3. So our numbers would be negative 4 and a positive 1. So this factors to x minus 4 and x plus 1 over x minus 4. Now, before you cancel, you need to find the points of discontinuity. So we set our denominator equal to 0 and solve for x. So x is equal to 4. This is our point of discontinuity. Since it cancels, this is removable. Graphically, this is going to be a hole in the graph. Okay. Now our domain, again, we want to break it up at that point of discontinuity. So we're going to go from negative infinity to 4, and then 4 to positive infinity. So this is how you find your points of discontinuity. Again, if you need help with this, please let me know.